Hello everyone, in this video I'm going to be introducing the scientific practice of mathematical modeling, specifically with using word problems or solving with equations. And in this video we're only going to be focusing on constant speed type of problems. And at this point we've already modeled constant speed and we've done it graphically, right? We've had a position versus time graph, and whatever the graph is, um, it's always been a straight line, right? Now that's important because the slope of this line is the velocity, right? And that would make sense that because the slope is constant, well, the speed, the velocity is constant as well. And the units for velocity are going to be meters per second in our case. Right. Now, this is a great model. It could help us in a lot of situations, but there's times where this model may not be the best, and we might want to use a mathematical model. Now, what's really cool is we get our mathematical model from our graph. So let me explain that. So we have a linear graph, right? And this is going back to algebra. If it's linear, because it's linear, right, we're going to have our equation be y equals mx plus b. Right. Now, what's cool with physics is that this isn't just like this arbitrary y or mx or b. This y actually means something in this case, right? That's our position. And so we represent position with an x. And on my x-axis, well, that's not just x, that variable's time, so I'm going to put a t there. And my y-intercept, right, whether it's 0 or it's anywhere else, well, that's just a type of position. Specifically, it's my initial position. So I'm going to put an x there, but then just put this naught right here, and that tells me that it's my initial position. The x on its own, that's its final position. All right, now m is the slope, and like I mentioned before, the slope of this graph, the units are meters per second. That is the units. Those are the units for speed or velocity. So my slope is my velocity, so I'm going to put v in there for velocity. So this is my equation. That's how we get it. We get it from the graph. Now there are going to be other times where we're going to want to use the same equation but written in a little bit of a different way. So what I could do is I could just rearrange the variables of this equation. Maybe I'm going to bring the initial position to the other side. And in that case, it would be the final position minus, so I'm subtracting from both sides, minus your initial position is equal to, and then there's still Vt on the other side. All right. Now, anytime I have a final minus initial, well, that's actually the one side of the equation for delta x, which means the change in position or the change in any variable is equal to the final minus initial. So I could kind of simplify it. Instead of writing just x minus xo, I could just write delta x, and that's exactly what I'm going to do. So I'm going to put delta x right here is equal to, and then I still have Vt right here. And here's another equation. So these are the exact same equation right here. They're just written in a different way where we've rearranged the variables. So why would we want to use one and the other? Well, it just depends on the situation. We haven't talked about this just yet, but this type of equation we're going to want to use for proportional reasoning. And if you're not sure what proportional reasoning is just yet, that is okay. That'll come in later. So let's apply this equation. What we have here is just a general template, and we could use this for constant speed, changing speed, or really any type of problem that's going to involve the scientific practice of using mathematical models. So let's go through the problem solving process with an actual problem. So a dune buggy starts at 2 meters and travels -4 meters in 10 seconds. Let's calculate the velocity of the dune buggy. Now, just going to make sure this is situated. Now, my first step, it says, what are we solving for? Right? Calculate the velocity of the dune buggy. It seems simple, but it's super important. We're trying to solve for velocity. That's our unknown. So the next thing it says is, hey, let's draw a picture and identify some known variables. So it says here that I'm starting at 2 meters. So maybe what I'll do is I'll kind of like almost like draw a number line type of thing. And I might mark this as 0. This is 2 meters, and this is -4 meters. Right? And we start at we start at 2 meters, and we're going to go towards -4. Right? So the picture really just helps us visualize what's going on instead of just kind of getting bogged down in the numbers. This picture also tells us a few things as well. So for instance, if I start at 2 and I end at -4, I'm going to the left, right? So even before knowing what this number is, I know that I should get a negative number, that my velocity should, since I'm going to the left, my velocity should be negative. All right, the next step is, well, the same step on number 2 is we're going to draw a picture, but then we're going to identify our unknowns. So it says here 2 meters. It starts at 2 meters, so that's going to be my initial position. Remember, x naught is initial position. All right, it ends, or it travels to -4 meters, so that's my final position, so just x. Right. And it does that in 10 seconds, so that's going to be the time, 10 seconds. And we'll be solving for velocity right here. So for step 3, now I'm going to choose the appropriate equation. And it's really easy in this case because we only have one equation. We're just going to use one of these. So we don't really need to worry about A and B for now. In this case, since I have my initial position and my final position right here, I'm going to use the top equation. Right. So x, this is going to be step 3. My final position is equal to Vt plus XO, or X naught. And the fourth step is kind of plug and chug. Match the variables appropriately with the equation. So X is 2, or X in this case is 4 meters, my final position. I don't need to worry about units here. My velocity, well, that's what I'm solving for. All right, time is 10 seconds. And my initial position is 2 meters. All right. Now, I purposely made a mistake here, and I don't know if you caught it just yet, but my initial, or my final position is -4 meters. So it's really, really important, and that's kind of where the picture will come in handy. It's really important that we use that picture, or we make sure that we're reading the problem carefully to realize, hey, it ends at a position of -4, because that would definitely change up our math, right? So now I'm just going to solve for velocity now. That's all I need to do. That's going to be step 5. So I'm going to subtract -2 to the other side. So -4 minus -2, well, that's going to be -6 is equal to my velocity times 10. Right? And then I'm just going to subtract or divide 10 by both sides. And my velocity is going to be -6 over 10. Right? Now we want to represent that as a decimal, though. So my final velocity is going to be negative 0.6, and then you want to make sure that you have your units as well. It's really, really important, and direction when appropriate, and it's absolutely appropriate here. I'm going to the left, -0.6 meters per second, and I've solved my problem. All right. So that's it for introducing mathematical modeling when it comes to constant speed.